In this module, we will begin our discussion on some of the aspects of waveguides and kind of finish this topic of waveguides. We will discuss wavelength, impedance, power calculation, and if the module permits, we will also talk about attenuation inside a waveguide. Well, we have been talking about waveguide and examining its frequency for different modes. We obtained expressions as also for that one. Sometimes it is quite interesting to actually look at the wavelength aspects of the waveguide. In some high frequency such as say 20, 30 gigahertz or above, or the 60 gigahertz waveguides, instead of quoting the frequencies, it is sometimes convenient to quote in terms of wavelength, and because of that, let us look at how wavelength and frequencies are related inside this waveguide. Okay. We already know that wavelength has to be defined is in terms of the phase of the distance between, or the distance between two points which have the same phase, right. So, that is the basic definition of a wavelength. We also know that this wavelength is related to a parameter beta, and we need to find out what is beta. We have already seen the relation for beta and gamma, right. Gamma is equal to alpha plus j beta, which would essentially be present for any mode. If the mode is lossy or if the frequency is less than the cutoff frequency, then alpha would be the dominant factor, beta would not be there. Whereas for the case when the wave is actually propagating, then gamma will be equal to pure propagation constant, right. So, for that to happen, we need to recall the relation between gamma and omega, and that relation is omega square mu epsilon minus omega c square mu epsilon under root. Since we know that this is gamma and the other way around, so this should be omega c square mu epsilon omega square mu epsilon. So, only when the frequency f or equivalently omega becomes greater than the cutoff frequency fc or equivalently omega c does this second term dominate the first term and convert gamma into a pure imaginary quantity, and that imaginary component would be the propagation constant beta, right. That would describe how the wave is propagating along the z direction and in terms of e to the power minus j beta z. So, the way to relate gamma and beta would be when omega is greater than omega c, you can take this omega square mu epsilon outside and then adjust this equation so as to obtain the propagation constant beta as omega square mu epsilon under root square root of 1 minus fc, since there would be cutoff frequency for different modes. So, let us just write this out as fc mn divided by f whole square. This is your beta, and omega square mu epsilon can be conveniently written as k, and therefore, square root of that one will become k. So, what is k? K is omega square root mu epsilon, and this would have been the propagation constant had we considered propagation in free space, right. So, in free space you do not have any other aspect to the propagation constant, you just have this k factor, and we saw that the fields would go as e power minus j k z, right. So, this is how they would have propagated, where k would be equal to omega into square root of mu epsilon, right. This is a free space propagation. However, in this case you see the propagation constant beta inside the waveguide is related to the free space parameter, but this free space parameter is getting multiplied by some factor, right. This factor takes into account that propagation will not happen when f is less than fc, the cutoff frequency. Okay. So, this is the propagation constant for the waveguide, which would be the propagation constant for the free space multiplied by this one. Of course, if you actually take the waveguide and start increasing the dimensions, you start expanding a to infinity and b to infinity, you would essentially end up with free space propagation, correct, because a going to infinity and b going to infinity will cause the cutoff frequency fc to go to 0. So, all modes would be possible, and that would correspond to free space propagation, but in practice of course a is never infinity or b is never infinity, and therefore, this situation does not really arise for us. What is interesting is that because we have bounded the waveguide, there would be certain cutoff frequency, and the frequency f has to increase this cutoff, has to go beyond this cutoff frequency. We know beta and lambda are related in terms of transmission lines or propagation constant of a transmission line, or for the free space we had calculated this beta and said beta is related to 2 pi by lambda, or beta is given by 2 pi by lambda. In this case, can I simply call this as 2 pi by lambda? Unfortunately, no. This beta corresponds to the propagation constant along z direction, right. This is the component along z direction, along the propagation direction, and along the propagation direction if you find out two planes such that the phase between these two planes is essentially the same. So, the phase of this wave here is the same as the phase of the wave component at this point. Okay. This distance should be called as lambda g. What is lambda g? It is the distance between 2 points along the waveguide. So, you have to imagine now, right. So, this is your waveguide component that I have drawn here. So, along the waveguide as you propagate, the distance between two components with same phase, equiphase distance would be the guide wavelength, wavelength along the direction of propagation or along the guide. So, this beta that we have obtained in terms of k and whatever this 1 minus fc by f, I am just dropping this mn for notational simplicity, but you should not drop that one. So, this fellow should actually be equal to 2 pi by lambda g, okay, which implies that lambda g can be written as 2 pi divided by k square root of 1 minus fc by f whole square. But I also know that 2 pi by k can be written because 2 pi by k is nothing but 2 pi by omega square root mu epsilon. Omega is nothing but 2 pi f, right. So, it would be 2 pi f times square root of mu epsilon, 2 pi goes away and 1 by square root of mu epsilon divided by f is nothing but wavelength in free space itself, right. So, wavelength lambda is the wavelength of the TEM waves, transverse electromagnetic waves, or the lambda in free space. Sometimes this lambda in free space is given by a notation lambda 0, 0 indicating that this is the free space wavelength. So, in terms of that lambda 0, I can write this expression for guide wavelength lambda g as lambda 0 divided by 1 minus fc by f whole square. Also, omega c will be 2 pi fc, omega will be 2 pi f, right, and the ratio of fc by f can also be related to the ratio of lambda, because lambda c would be 1 by fc and lambda itself would be 1 by f. So, you can rewrite this expression in the denominator as well, but you do not have to really do that one. What is interesting is that the guide wavelength that you have obtained is actually greater than the free space wavelength lambda 0, right. So, if you were to plot this guide wavelength as a function of frequency, right. So, if you plot this one as a function of frequency, so the wavelength in free space, this is how it would go, right. So, at f is equal to 0, the wavelength would be around infinity, and thereafter it is a 1 by f kind of a relationship. The ratio of these two at any given point would give you the free space velocity as well. However, for the waveguide, nothing would propagate until you reach the fundamental mode, and thereafter you will start getting the higher order modes, right. So, before this wavelength is itself not properly defined, and thereafter the wavelength will be defined in the same manner. It would actually start at a particular value, at f is equal to fc, it would be infinity, and thereafter it would start to converge like this. As this frequency increases, higher order modes would begin to propagate and you start getting different kinds of lambda g. So, this is lambda g of 1 0, this is lambda g corresponding to 2 0, the next higher order mode, and this one would be lambda g corresponding to free space, in which case this would also be equal to lambda 0, right. So, for the free space, guide wavelength is equal to the free space lambda g, and this would, because of 1 by f, they would all start to drop, and of course, at f much larger or f tending to infinity, the wavelengths all would converge towards one another. This is the guide wavelength. Okay. The cutoff wavelength can also be obtained as lambda c given by c by fc, where c is the free space propagation, assuming that the waveguide is filled with air, okay, or even if the waveguide is filled with something else, you can always take this as the definition, and what it implies is that for the waveguide to have propagation, f must be greater than fc, so that gamma is equal to j beta. Because lambda and f are inversely related, the same condition means that lambda must be less than lambda c for the same condition to occur. Okay. So, fc 10 would correspond to the minimum frequency, right, before which the propagation does not begin. Correspondingly, lambda c 10 corresponds to maximum wavelength. Okay. If the wavelength happens to be less than this, then only the wave would be propagating. If the wavelength happens to be greater than this, then that particular mode would not propagate. since Fc10 is given by UTEM divided by 2A, as you can see in the last module that we discussed this one, lambda c cutoff wavelength for the TE10 mode would be given by 2A itself. Okay. So, this is actually the 2A condition. At this 2A, you will be able to obtain the fundamental mode, which will have one half cycle variation along x or along y walls. Okay. So, along these walls you will have one half variation, and that half variation comes because you have chosen lambda c as 2A, right. So, this is the maximum lambda that you can have. Anything else that would not correspond to a propagating mode. Let us look at a simple example. This example is to illustrate calculation of these quantities. There is not much of an interest in this example other than that, but these calculations are important for you because you need to get some proficiency in calculation of cutoff frequencies and cutoff wavelength. Okay. Take A is equal to 1 centimeter, B is equal to 0.6 centimeter waveguide. Clearly A is greater than B, and we know that the fundamental mode will be TE10. Because A is greater than B by it is also greater than square root of 3B, we also know that the next higher order mode will be TE20. Can we calculate what are the cutoff wavelengths for 10, cutoff wavelength for 20, and also calculate the guide wavelength lambda g and compare that one to the free space wavelength. Okay. Assume that the waveguide itself is operated at a frequency of 18 gigahertz. Okay. So, frequency of the generator that we connect to the waveguide is 18 gigahertz. First question, will this 18 gigahertz correspond to propagating mode or will it be attenuated? To obtain that one, we need to know what is Fc10, okay, or equivalently one can try to find out what is lambda c10. Lambda c10 is equal to 2 times A is 1 centimeter, therefore this is 2 centimeter, correct. Similarly, lambda c20 would correspond to, because Fc20 is nothing but 2 times Fc10, lambda c20 would correspond to lambda c10 by 2, which would be 0.5 into 2 centimeter, which is 1 centimeter. Okay. Let us now look at lambda 0, which is the free space wavelength. If the free space wavelength corresponding to 18 gigahertz happens to be less than 2 centimeter but greater than 1 centimeter, then this would be operating in the TE10 mode. Other than if it is less than 1 centimeter, both modes would be operating. So, let us look at that one. Lambda 0 is given by C divided by 18 gigahertz. 18 gigahertz is 18 into 10 to the power 9. C is nothing but 3 into 10 to the power 8, and if you do this calculation you will get this as 1.67 centimeter. So, clearly 1.67 centimeter happens to be between 1 and 2 centimeters. This is lambda c10, this is lambda c20. So, this particular waveguide is operating in the TE10 mode, as we can see, and its lambda 0 is given by 1.670. So, this is actually a single mode propagation, only TE10 mode is propagating. What is the corresponding waveguide lambda g waveguide length? Lambda g is nothing but lambda 0 divided by 1 minus Fc10 by f whole square, right, or equivalently one can find the relationship in terms of lambda also, but Fc10 is easy to calculate. This is C by 2A, which is nothing but 15 gigahertz in this case. Okay. So, you can obtain what is lambda g by substituting into these expressions, and you would get this as 3.02 centimeter. So, you see here the free space wavelength is 1.67 centimeter, the guide wavelength is 3.02 centimeter. Okay. The waveguide wavelength is significantly longer than the free space wavelength, because the waveguide is kind of operating very close to 15 gigahertz, right. So, it is actually operating quite close to the cutoff frequency, and therefore, the waveguide lambda g would be quite large. You can see that one from this picture, right. So, because you are operating very close to the cutoff frequency, so you take a look at this one, you are operating very close to the cutoff frequency, lambda g would be quite large compared to lambda 0. However, if you operate at a higher frequency, then lambda g would correspondingly come close to lambda 0. Okay. Now, at this point it is customary to discuss phase velocity and group velocity. but I would like to have a unified discussion of phase velocity and group velocity as a separate module. So, I will not introduce that waveguide phase velocity and group velocity in this module. We will calculate that one and we will discuss the significance of these calculations after we have looked at dielectric waveguides. Okay, as a separate module we will be talking about. So, we will now discuss impedance of the waveguide. So, for the impedance definition, you remember that for the free space we had defined it as the ratio of transverse electric field component to the transverse magnetic field component, and the same expression will be used even for this waveguide as well. You have to define impedance as ratio of magnitude of the transverse electric field component to the magnitude of transverse magnetic component. Let us try to find impedance for the TE case. For the TE case, I know that Ez must be equal to 0, and if you go back to the expressions for Ex, Ey, Hx and Hy that we obtained in terms of Ez and Hz, you have to go to those equations which we couple of modules earlier, and then set Ez is equal to 0. So, when you set Ez equal to 0, you see that Hex will be equal to j omega mu minus j omega mu divided by h square del Hz by del y. You will also find out the corresponding Hy component to be equal to minus gamma by h square del Hz by del y. Now, you take the ratio of Ex to Hy, and what you find here is that you will see that this minus sign will cancel with each other, del Hz by del y will go away, and what you are left with is that j omega mu divided by gamma. Okay. So, this is your ZTE, okay, and similarly you can find out what would be ZTM. What would be ZTM? For the TM case, Hz must be set equal to 0, and you will have corresponding components for Ex, let us say, given by minus gamma by h square del Ez by del x, and then you will have Hy which would be minus j omega epsilon divided by h square del Ez by del x, again taking the ratio of these two. So, this is ZTE which we want to write down. Similarly, for ZTM will be equal to the ratio here, minus sign again will cancel, h square will cancel, what you get is gamma by j omega epsilon. Okay. These equations allow you to write down the corresponding transverse components in terms of the impedances. Of course, the ratio of Ex to Hy must also be the ratio of minus Ey to Hx in both cases, because you go back to those equations and you will see that this is exactly the case. So, the transverse electric field component for TE, I will leave the TM as an exercise to you. ET is given by x hat Ex plus y hat Ey, okay, and the corresponding H components can be written in terms of the waveguide impedances as Ex is related to Hy, right, and Ey is related to minus Hx. So, you can write this as 1 by ZTE, along x would be minus Ey plus Ex, because Ex and Hy, so Ex y hat. Okay. So, this is the advantage of obtaining the impedance. Now, once you obtain the impedance, you can actually calculate all the other quantities as well. You can also see that the dot product of these two is actually equal to 0, right, because we see that E dot H for the transverse components is equal to 0, indicating that these components are perpendicular to each other or mutually orthogonal to each other. We can also use them to relate, because of this minus and plus kind of reminding you of a cross product. You can find out what is Ht in terms of the cross product corresponding to the propagation direction z and the transverse component, this divided by 1 by ZTE. Just as we had done for the case of a free space propagation, you can express the H component in terms of the curl or the cross product of Z and E transverse components. You can check that this equation checks out for both waveguides as well as for free space. In free space, you need to replace this ZTE by Z0, which is the intrinsic impedance of the medium, right. So, if there was no factor of Fc in that particular free space case. Okay. As I said, similarly you can find out Zm, but going back to what ZTE is, ZTE we obtained was j omega mu by gamma, right. So, when the waveguide is actually propagating, I know that gamma can be written as j beta, right. So gamma would be equal to j beta, therefore I can write this as j omega mu by j beta. J will cancel with each other and the impedance turns out to be real, okay. But what is beta? Beta is nothing but omega square root mu epsilon, which is what the free space component would be, times 1 minus fc by f whole square. So corresponding to a particular cutoff frequency calculation m and n, this would be 1 minus fc by f whole square. Omega cancels, mu and square root of mu will cancel one of them and pull the square root of mu onto the numerator, and what you get is the free space wavelength eta, as we had written down, divided by square root of 1 minus fc by f whole square. What about ZTM? Well, ZTM can also be calculated. ZTM is nothing but gamma divided by j omega epsilon. So substitute for gamma as j beta, again j will cancel and the impedance turns out to be real, and beta is nothing but omega square root mu epsilon, the free space part, times 1 minus fc by f whole square, right. Omega epsilon is there, omega cancels, from the square root of epsilon cancels in the numerator, that square root gets transferred to the denominator, and what you get is eta into square root of 1 minus fc by f whole square. In case someone has calculated ZTE and ZTM for you, and if you want to calculate what is the intrinsic impedance of the mode, you can find out ZTE times ZTM will be equal to eta square, okay. So once you have this equation, you can actually find out what is eta. Now you might say that, well, if I want to calculate what is eta, I would calculate what is ZTE. If I want to calculate ZTE, I need to know eta. If I want to calculate ZTM also, I need to know eta. The answer is that, so why is this equation important? The answer is that for a waveguide, it is kind of easier to calculate the ratio of the transverse E and H fields by making appropriate measurements, and from there find out what is eta, okay. This is especially true when you cannot really access the material that is sitting in between the waveguide, okay. Because of that reason, it is sometimes easier to calculate ZTE and ZTM. From that, make an estimate of eta. From that eta, you make an estimate of mu and epsilon, okay. This kind of an inverse way of finding out the material constants is quite common at very high frequencies and especially at printed circuit boards, okay. So something that we were not discussed at this point, if you want to sketch graphically how this ZTE and ZTM goes, well, they would all converge to eta for f much larger than fc. You can see here that for f much larger than fc, this term will be equal to 0, right, and then ZTM will converge to eta. However, when f is less than fc, there won't be any component here, and then the ZTM would actually be equal to kind of minus infinity. Similarly, ZTE will be equal to plus infinity, and propagation would begin at appropriate cutoff frequencies, okay. So you would actually see that this is how the corresponding ZTE and ZTM impedance values will vary. Let us discuss one final aspect. We will discuss what is called as power calculation, or we want to know what is the transmitted power when we excite a particular waveguide mode. As before, to obtain the power, we go back to Poynting theorem or the Poynting vector. The Poynting vector would have a certain average, certain power density S. From the power density, we will calculate what is the actual transmitted power. So the transmitted power P is given by integral over an appropriate surface that you have to choose. We will choose that one very shortly. And then what is the Poynting vector, and integrate this Poynting vector over the surface that you have chosen, right. So this will give you power in watts. Poynting vector itself will give you power density. What is power density? For this case where you have expressed electric and magnetic fields as a phasor, it would be half real part of E cross H complex conjugate, right. So this calculation you need to perform and then substitute for E and H. Immediately you can see that if E can be broken up into its transverse, okay, and its longitudinal component, similarly break up H as transverse, okay, H component and the longitudinal H component, okay. What you can see is that since the power needs to be transmitted or taken from the mode from one place to another place on the waveguide, what is interesting is not the longitudinal components, but it is only the transverse components, right. Since these are the only things which are interesting and these relationships are already known in terms of the impedances, you can safely substitute for the impedance and then relate E and H and obtain this expression. What we mean here is that Ex is given by ZHY and Ey is given by minus ZHY, right, because Ex by Hy is Z and Ey by Hx is equal to minus Z. You can actually write down what is this E cross H complex conjugate in terms of this Z and Z complex conjugate. H will be Ex by Z along Y minus, and then you will have along the X component to be Ey by Z along the X component. This would be your magnetic field, transverse magnetic field. For the transverse electric field, it would be X hat Ex plus Y hat Ey, right, and this would be the electric field, transverse electric field component. Now you try to find E cross H, but then remember that when you find E cross H, H has to be complex conjugated. So when you do all that, you will see a simple relation as half real part of 1 by Z complex conjugate, which would be the complex conjugate of the impedance Z itself, and integral over Ex square plus Ey magnitude square dx dy. For the waveguide that we had in this way along the Z direction, I have chosen the surface to be something along X and Y plane. It makes sense, right, because with this chosen surface, the power will be carried along Z direction. So you are interested in power being carried along Z direction, and therefore it would be wise to choose the surface, the open surface, to be that along X and Y, encompassing the walls, okay, just below the walls, but encompassing almost the walls for the calculation over here. For the TE10 case, which is very important, right, we know that we have only Ey and Hx components and Ex component is 0, and Ey component is given by minus j omega mu H0 a by pi sine of pi by a into x, right. So this is what Ey is given to be, and this is enough for us to calculate the power carried. So P will be equal to half real part of 1 by ZTE corresponding to the cutoff frequency of 10, right, times integral over the surface dx dy, and then put this Ey square, that would be omega mu H0 a by pi, all these quantities mod square, okay, times sine square pi by a into x. We already have seen dx and dy. Now along y you assume y equal to 0 and y is equal to b, and for x you assume x equal to 0 to x equal to a, although you just have to consider the surface to be slightly less than that, but it doesn't really matter if you consider this to be x equal to a rather than slightly less than a, okay. So because of that reason we will consider the wall as x equal to a. Integration over y will bring out b into picture, and then integrate this sine square. After rewriting that in terms of 1 minus cos 2 something, you carry out this integration. You also know that ZTE turns out to be real, right. So ZTE turns out to be just omega mu by beta, where beta corresponds to 10. Do all this simple calculation. What you get here is AB by 4, okay, omega mu beta 10, beta 10 corresponds to the propagation constant for the dominant mode TE10, times H0 magnitude square a by pi whole square watts. In fact, because beta 10 can be related in terms of Fc and F, you can rewrite this one in terms of the frequency as well. So you can write this as AB by 4 eta E max whole square, okay, times square root of 1 minus Fc10 by F whole square. What is E max here? E max corresponds to this amplitude, okay. E max is omega mu a by pi times H0. This is simply to set a certain constant to simplify this one, but if you know how much power you are actually putting into the waveguide, then you can calculate what is E max. You know what would be the operating frequency for your waveguide mode, so you know F, you know A and B, the dimensions of the waveguide, you know the intrinsic impedance, assume that it is filled with air or some other material, you can find out what is Emax, and from Emax you can find out H0. Remember, this was the only constant that we had not been able to pin down from boundary conditions. Boundary conditions allowed us to write down whether A, B, C or D would exist, and whatever that would remain would we put everything into under H0 or E0 depending on which modes we were analyzing, and to pin down those H0 or E0 values you have to use the power condition. So you know how much power you are putting in, then you will be able to find out the amplitudes H0. Okay. Such calculations are quite simple, but something that you might have to try it out once or twice to just get familiar with this one. Okay. So if you plot this power that is transmitted as a function of frequency, clearly when f is less than fc10 there won't be any power to be propagating. At f is equal to fc10 barely any power gets propagated. So this would be fc10, this is the f axis, and as f becomes very large this factor becomes equal to 1, and then you would reach to AB by 4 eta Emax square, right. So this would be the asymptote value to which you would reach, so as you start increasing the power. Okay. This would not be completely correct because this only assumes that TE10 mode is the one which would be propagating throughout the frequency, but we do know that after some time FC201 start propagating, then you have TE01, then you have TEM11, TM11. So all these things would actually drop the power. In other words, they would also start carrying some amount of power, and if your operating frequency happens to be say here, then you actually have power distributed in 3 different modes. So some power carried by the fundamental, next power carried by the next higher order mode, and the other higher order mode. So all these would share power depending on how much power you have put in and what are the corresponding factors for FC10 and F that you have to calculate. So if you want all the power to be concentrated within, you have to operate it only in the fundamental mode, but at that point your waveguide is not actually carrying maximum energy. Okay. What would happen when omega is less than omega c? Well, all the modes would be cut off, right. So the quantities would only be attenuation, and when you launch some power with an operating frequency f less than fc, nothing would be carried by it and everything would be just attenuated. Okay. So we stop at this module and we will consider the power attenuation calculations in the next module.